In this video, we'll talk about the generalized power rule and general derivative rules in the context of the chain rule. So the idea of these rules give you an easier way to handle derivatives of certain types of functions. And they all really just come from the chain rule. So if I have a function u of x, how do I differentiate the function u of x to the n? Well, this is a pretty standard form from the chain rule. This is something to the power n. I differentiate that by saying it's n, that thing, to the n minus 1, and then times the derivative of the function that's inside. Right, that is the chain rule applied to this composition here, where my function f of u is u to the n, and u is just this u of x that I had there in the first place. So a way we can write this is saying that the derivative of u to the n is n u to the n minus 1 times du dx. Using Leibniz notation here, but it gets the same point across. If I differentiate the function that is u to some power n, what I get is n times u to the n minus 1, the derivative of the nth power function, and then by the chain rule, times the derivative of what's inside, which is here is du dx. And you can do this for really any function that you know how to differentiate. You can put a u inside it instead and get the same sort of results by the chain rule. What kind of things do I get here? For instance, the one we had before, the derivative of u to the n is n u to the n minus 1 du dx. I can do something with like sine of x. The derivative of sine of u is now going to be the derivative of the sine function, which is cosine of u times du dx. Again, just by chain rule. This first part here is the derivative of the outside function, which you know how to do because it's a simple outside function, plugging in u, and then times the du dx on the end, which comes from the last bit of the chain rule, this u prime term. I can keep going, say for cosine of x, right now put in cosine of u, this is negative sine of u du dx. Other trig functions all work the same way. You could do something like e to the u. This is just e to the u because that doesn't change when I take derivative, times du dx. And so on down the line. Really, any formula you have for a derivative function, you can put it in this form as an application of the chain rule. You don't need to have these sort of separate because they really are just direct applications of the chain rule. But it's nice to know that you can also write them in this way if you want a simpler way to express certain properties you know about functions. The other thing to emphasize here is that for each of these cases, this du dx term is always multiplied on the end. It's multiplied. There's nothing else we're going with the du dx term. It's always pretty easy to isolate. This is on the end. It's multiplied by something that's pretty complicated, right? Cosine of u is a complicated function. Du dx is a multiple of that function. So as a coefficient there, it sort of sits by itself. Now it becomes super important when we're trying to use this chain to do other things later on. Knowing that this du dx term always pops out on the end on its own means we can do more things with it for different types of problems. That's the idea of the generalized power rule and generalized derivative rules as applications of the chain rule. Really, they are just applying the chain rule to certain types of functions, but depending on the form you want to see things in, this could be a nice way to organize your thoughts about how the chain rule works on different types of functions.